Great. Okay, so thank you for the organisers for inviting me to give this talk. We haven't heard too much about stars yet. I was here in the early 1990s and then again in the late 1990s, first as a PhD student and as a postdoc. And I have very happy memories of this place. I completely agree with Richard Ellis's comments on Tuesday about how this was a wonderful place to be in the 1990s. My particular PhD year, there were 17 new PhD students, which was a record at the time. I don't know whether it's still a record or not, but it was a great place to work. My first memory of the IOA was after flying in from New Zealand. I came here on a Monday morning and turned up at the reception and I said, I'm one of your new PhD students. And they said, oh, we're not ready for you yet, come back next week. So I remember that very clearly. I remember a few other things as well. We had to choose PhD projects, and you might wonder how I got into star formation. And there are other interesting projects around. I particularly mentioned Arthur Lahav's project. He had a project on using neural networks to classify galaxies. And I was quite interested in that because I'd done a summer project in New Zealand on what was actually a sort of forerunner of the natural language AI that we have today. So I was kind of interested in that project. But in the end, Kathy showed me a simple plot of the eccentricity distribution of binary stars versus their separation, and asked me, why do you think they have this eccentricity distribution? And I got interested in that problem, and that was how I ended up working on binary star formation with Kathy, and the rest is like 30 years of history. So speaking of history, so I first made this slide for a talk I gave here in Cambridge in 2013 with a title, of course, that was tailor-made for Cambridge. But I think this is still relevant for the point of this talk, which is about star formation and where we are at the moment and where I hope we'll be over the next few years. And you might also wonder, why have we got a talk about star formation right after a talk about high redshift galaxies? But I hope by the end of it, you will realize that they are actually very closely linked. Star formation is less than 100 years old in the sense that before we knew that stars were powered by fusion and we knew the lifetimes of stars, people thought that stars were formed when the universe was formed. But then, of course, the most massive stars don't live that long. So we knew that the most massive stars had to be forming in the universe today. And so I sort of think of that as the first age of star formation, if you like. The second age, I'd say, is sort of 1950s through to 2010-ish or so, where we were looking at some of the main processes involved in star formation. So the collapse and fragmentation of molecular clouds. This goes back to papers from Fred Hoyle, for example. And then other effects such as magnetic fields, magnetic support, radiation transport, etc. And so investigating different processes. And then from 2012 on, I want to argue that we're in a new age now, the third age of star formation, where we can actually hopefully make predictions about stellar properties. And of course, a lot of this has come from the increase in power of computer simulations, which of course Jim Stone talked about in his talk earlier in the afternoon. If you have a star, we all know that the main thing that matters, its primary property is its mass. That basically determines everything you need to know about the star. If you have a stellar population, then it's probably the distribution of masses, which of course for a zero-age population we think of as the stellar initial mass function. This, as a sort of typical form here, I show the Chabrier IMF, but there's Krupa ones and so on. There's a salpeter type slope at the high mass end, and then some sort of turnover towards low masses, and the typical star has a mass of a few tenths of a solar mass, so a M dwarf. And this slope here is steep enough that most of the mass is actually in the low mass stars, while most of the light comes from the high mass stars. And so that gives you a mass to light ratio, and we'll come back to that later in the talk. Now, one of the interesting things is that if you look throughout our galaxy, and in fact nearby galaxies where you can actually resolve the stars, people have looked at does the initial mass function vary? And at least locally, there's very little evidence that it does vary. It always seems to be the same. And I think just over the last 4 days, I've been quite interested in who's mentioned the IMF and in what context. And most people just assume that the IMF never varies, okay? And if you know, there's good reason for that. It doesn't seem to locally. But for a theorist, that's really annoying, right? Because if you're trying to understand the physics that goes into forming the IMF, you want to come up with a theory, and then you want to predict where that theory will break down and you get something different, and then you want to go out and test it. But if nothing ever changes, then you can't do those sorts of tests on your models, okay? The second main property of a stellar population is probably multiplicity. And we heard a lot about multiple systems and the sort of exotic things they give you in the universe on Wednesday morning. In terms of multiplicity, most massive stars are in binaries or even higher order multiple systems. But when you go down to M dwarfs, for example, most of those are single. And then there was this interesting result about 5 years ago now that for very close binaries, so spectroscopic solar type stars, there's this anti-correlation with metallicity and frequency. So stars like the sun, the spectroscopic binary frequency is about 15%. But if you go to very low metallicities, it jumps up to about 50%. So about half of solar type low metallicity stars like the sun are in very tight binaries, which is interesting. And I'll come back to that in a few minutes as well. So the fact, of course, that the IMF never varies doesn't stop theorists, okay? So there's been many, many theories about where the IMF comes from. I think one question you can ask is what sets the overall mass scale? So why does the typical star have a mass, or in the M dwarf regime, why aren't most stars, say, brown dwarfs? Or why don't most stars have 100 solar masses? And I think fundamentally this comes down to thermodynamics. And again, this comes back to the Institute of Astronomy and indeed before that with Fred Hoyle's work, and then of course Donald Lyndon Bell and Martin Rees in the 70s, looking at the minimum mass of a star, which is in the sort of planetary mass regime, typically thought to be a few Jupiter masses. And then some of my work, for example, looking at the influence of radiator feedback as you're forming stars and how that alters the mass function, which again I'll mention in a few minutes. So there's the overall mass scale. The other thing then is what gives this shape. And I think there's two main classes of model here. One basically says, well, the interstellar medium is very turbulent. That turbulent breaks up the clouds into clumps, and then when those are gravitationally unstable, they collapse. And so maybe basically you get a mapping from the cloud structure into the IMF. And so you can develop models along those sorts of lines. And then the other class of models are more dynamical type models, looking at the accretion rates of stars, how those accretion rates might vary with the stellar mass, or how long stars accrete for. And so you can develop models based on the sort of competitive accretion, which Ian and I worked on in the 90s as well, where most of your stars end up with low mass just because they don't accrete very long. They're involved in, say, a dynamical interaction which kicks them out of the dense gas, gives them a low mass, whereas you end up with very few stars accreting for a long period of time and actually work their way up to a high mass. Okay, and one of the interesting things about all these theories is they don't simply produce invariant IMFs, all right? So this observation that the IMF never varies does not simply come out of these models at all, right? They all, in their simplest forms, predict that the IMF should vary all over the place, okay? Okay, so simulations, what can they tell us? So 2012 was in my timeline of history, and the reason for that is this was the first calculation that I did here, which produced a realistic stellar population, all right? So we're talking low mass stars here, unlike Carlos tried to tell you this morning. I still can't tell you much about the high mass end of the IMF, but I hope I can tell you a lot about the low mass end of the IMF. Anyway, so these calculations is about a parsec across around 500 solar masses of gas, formed about 200 stars and brown dwarfs. The key is that it forms all stellar systems, so right down to very low mass brown dwarfs, and also disks as well, which I'll mention in a minute. And I don't know if you're watching this movie here, but this is gas temperature here, and you saw that as the stars form, they heat the gas around them, and that alters the subsequent star formation, which again I'll mention in a minute. But just to convince you that this gives you a reasonable stellar population, so the mass distribution of stars up here is compared to the Chabure galactic IMF. This is multiplicity as a function of primary mass, which you can see we recover the strongly increasing function of primary mass. Also, if you look at many of the stellar properties, the binary properties and so on, they're in good agreement with observations as well. And one thing I want to mention is where I think this comes from, okay? And so I think you need three things which all rely on interactions between stars as they're forming. So you need to form stars in groups so that they can interact while they're forming. But exactly how you form the groups and what the turbulence like, I don't think it really doesn't matter. Once you've got groups of stars, then you need dissipative dynamical interactions between accreting protostars. So as they're forming, they're interacting with each other dynamically, right? That gives you an IMF-like mass distribution from these sort of competitive accretion type arguments. And it also leads to this observed multiplicity as a function of primary mass and other stellar properties as well, because you've got, for example, if you form a low mass binary and then you have a higher mass star coming in, the most common result of that is that the massive star will exchange into the binary, kicking out the low mass star. And if you do that over and over again, then basically you end up with most of your low mass stars being single and most of your high mass stars being in multiple systems, okay? And then the last thing is that you also need radiative interactions between stars as they're forming. And I think this is the key to getting an almost invariant IMF in our galaxy. And I'll explain a little bit more about how it works in a minute. I don't think that other effects like magnetic fields, outflows, etc., are that important. Now, that's my opinion. Not everyone agrees with that, but at least that's where I stand. So another way of looking at the movies which you've just seen. So this is the same movie, the same simulation, but looked at a different way. So this is a 400 by 400 AU box around every star or brown dwarf that forms in the simulation. And you can see here what you couldn't see on a large scale. The resolution here is enough that we can form binaries, multiple systems, and disks down to sort of AU scales in these simulations. And you see the enormous diversity of systems that you form, but also the chaotic interactions. So you've got orbital decay forming close binaries. You've got this disk here, which is accreting material with a different angular momentum vector with time. So you see the disk plane rotating through about 120 degrees, I think it is. So all sorts of things going on very small scales in these simulations, right? And amazingly, if you look at the mass distribution and the radius distribution of these disks, that again matches what we see in our stellar populations in our galaxy, okay? And so this graph here was shown or this figure was shown earlier in the conference, is the cumulative distribution of the masses, dust masses of disks around young stars. The youngest stars, we think, are these class 0, class 1 objects. The simulations are best matched to those. And if you plot the masses of the disks from this 2012 simulation, which I only did in 2018, in fact, the data didn't exist from the observers before that, then you find very good agreement. And then my PhD student, Dan Alcindor, and I looked at disk radii as well. And again, you see amazingly good agreement. And just to emphasize, there's no magnetic fields in these simulations at all. And I'm comparing simulation here from 2012 with data sets from sort of 2020 or so. Okay, and so what I've hoped I've convinced you in this sort of first half of the talk is that we can reproduce at least low mass stellar populations which are in good agreement with the observed properties in our galaxy. And we don't need too much physics. We need self-gravity, hydrodynamics, radiative transfer, and sort of AU scale resolution in order to do that. And so the question now is, what can we do in terms of predicting stellar properties in other environments, all right? And so the first thing is, Naively, many of these semi-analytic models predict that your characteristic mass scale depends on the gene's mass in your molecular cloud. And so, for example, so the gene's mass, as we all know, scales with temperature to the 3/2 power and density to the -1/2. So if you run a calculation which is 100 times more dense, which is what we've got from here to there, then you expect that the characteristic stellar mass goes down by a factor of 10, right? Square root of 100. All right, and so my PhD student Michael Jones and I did some calculations back in 2018 where we did calculations 10 times and 100 times more dense. And what you find is that the characteristic stellar mass does vary slightly with density, but it's much shallower. It's something like rho to the -1/5 rather than rho to the -1/2. So if you change your cloud density by a factor of 100, you do get slightly low mass stars, but only by about a factor of 2 or so. Okay, so it's very resilient against these sorts of changes. Why does that happen? So I have a sort of cartoon which hopefully explains roughly why that is. So you can ignore the words here and just look at the cartoon. Basic idea is if you have a low density cloud, you all know the gene's length is very large and the typical masses that you form are fairly large, at least compared to a higher density cloud where the gene's lengths are all shorter and the associated gene's mass is smaller, okay? Now think about this effect of radiative feedback. Say this star in the low density cloud forms before these other ones. It heats up the gas around them and stops those from forming. So the mass that would have gone into 5 stars only goes into 1 star, okay? A little bit more massive because you've got the mass of 5 going into 1. All right, what about over here? Now remember these stars naively would be much lower mass here because it's a lower density cloud. This time, this one forms first. Here you've got 9 of these stars going into 1. But of course, because there's 9 going into 1 here, and these start off with lower masses, and here there's only 5 going into 1, and they start off with higher masses, this erases this effect of the characteristic stellar mass on the initial density of your cloud, so the initial gene's mass. Okay, so things are relatively invariant to density. What about metallicity? I've emphasized a little bit that thermodynamics matters. So if you change the metallicity a lot, maybe that changes stellar properties as well. And so you can argue, for example, that at subsolar metallicities, the molecular gas is generally hotter. It's bad at cooling, all right? Gene's mass increases with temperature, so you don't have as much fragmentation and your stellar masses should increase. But you can also say, well, subsolar metallicities, you've got reduced opacities. That means that collapsing gas remains optically thin and is able to cool rapidly to higher densities. At higher densities, your gene's mass is lower, so you should get more fragmentation and lower stellar masses, okay? And these are 2 perfectly valid arguments, and you don't know which one wins until you do the simulations. Now, early simulations showed that there was no strong dependence of the IMF on opacity. But a bit more recently, 2019, I did these 4 calculations here. So you've got metallicity. So this is still in the dust-dominated regime for the cooling. Okay, we're not talking POP3 here. But at low metallicities up to supersolar metallicities, same calculations except for the metallicity. And you can see this is what you expect, right? At low metallicities, your gas is quite hot. At higher metallicities, your gas is cold. Black here is sub 10 Kelvin, basically. And the gas is cold here both because of the extinction of the interstellar radiation field and also just it's really good at cooling because there's tons of dust and heavy elements around, okay? And so you think, well, okay, this must have an effect on the IMF, right? Wrong, okay? No effect on the IMF at all. Okay, so these are cumulative IMFs, all right? And all 4 calculations are on top of each other here, and they're also on top of Gilles Chabriot's parameterization of the galactic IMF. So we get the right IMF, and it does not depend on metallicity, even though you vary the metallicity by a factor of 300, okay? Okay, and so why is that? Well, we do have hotter gas on large scales. You saw that in the movie, but this is counteracted by these lower opacities on small scales, okay? And so you get collapse further down to higher densities that can still fragment, and that just happens to cancel each other out, which still amazes me. And I think, I wonder if there's a greater reason here. But anyway. Okay, so one thing that does change, thanks, is you do, though, reproduce this metallicity anti-correlation of close binary frequency with metallicity, okay? So this was actually, it was hidden. Well, it wasn't hidden. I just hadn't looked for it in the 2014 calculation, but when these observational papers came back, I looked back in the 2014 results, and it was actually there already, okay? And so we reproduced this anti-correlation of binary frequency with metallicity. This comes both from this enhanced small-scale fragmentation and also a more subtle effect that when you form stars, you go through a first hydrostatic core phase. This is a phase that only lasts a few thousand years, a big fluffy blob that forms before your stellar core. And the lifetimes of these first hydrostatic cores, as Larson called them, depends on the opacity. And so at low opacities, these cool very quickly and collapse to form your stars, so they don't give much time for these to merge. But at high opacities, these last a long time, and you've got a lot of time for close objects. Instead of becoming close binaries, they merge together and give you this reduced binary frequency at high metallicities. Okay, so IMF still doesn't vary, okay? What about at high redshift? Okay, and here you can see the link to the previous talk. Okay, so for a long time, there's been a lot of evidence that the IMF might vary early in the universe, all right? And so I don't have time to go through all of this, but people have talked about top-heavy IMFs and bottom-light IMFs, and my favorite at the moment is the intermediate light IMF, all right, But anyway, so this may require the IMF to vary. And then, of course, we've just heard about these JWST observations of young galaxies. The first papers that came out, as Carlos mentioned this morning, were saying, well, these galaxies' masses are higher than the baryonic masses in the halos, which, of course, is physically impossible. Okay, that extreme result in interpretation has gone away. But nevertheless, if you change your IMF here, you change your inferred galaxy mass as well. So, does the IMF vary with redshift? So I published this paper last year, Bate 2023. Again, this is not primordial star formation. I'm still talking here about star formation where it's dust dominating the cooling. But for example, if you go to Z equals 5, redshift of 5, the cosmic microwave background radiation is 16 Kelvin, which is much hotter than present-day molecular clouds, right? It scales as 1 plus Z, all right? And this, you might then think, alters your stellar properties. And indeed, this time you'd be right. Okay, so these are 100th solar, 10th solar, and solar. The movie here looks very similar. You've got hot gas, okay, not much changes. But here at high metallicity, there's no black anymore, all right? And that's because of this temperature floor, which is provided by the cosmic microwave background temperature being up at 16 Kelvin. Okay, and so this inhibits fragmentation, gives you less fragmentation than it does at present day time, Z equals 0. And so what that means is your low metallicity mass functions are very similar to what you had in the present day star formation calculations. They don't really change, but at high metallicity, your characteristic mass moves to higher masses, and you can see you become bottom light. It's basically no brown dwarfs and reduced low mass stars, all right? And if you look at the mass to light ratio here, it's about 10 times smaller for this than it is if you just use a normal Chabrier IMF. Okay, so I'm going to skip over that and just say that since that paper last year, what I've been doing is mapping out how the IMF and other stellar properties vary with redshift and metallicity. So I've done calculations now up to Z equals 10, and metallicities, well, actually up to 3 times solar as well. And you can see here that basically as you go to either high redshift and high metallicity, you come increasingly bottom light, all right? And so the idea here is we can then parameterize this. So these dots here with the error bars are the numerical results essentially for the characteristic, the median stellar mass in the IMFs that you get out. And you can then infit empirical functions here, which show you then how you can then put this into a galaxy formation model, for example, and use this to generate your stellar populations as a function of redshift and metallicity. And here I give mass to light ratios. Okay, so one here would be the normal mass to light ratio for a zero-age Chabrier IMF. But as you can see here, if you go to high metallicity and high redshift, then you can get very, very much lower mass to light ratios. So for example, at Z equals 10, if you have star formation going on at 1/10 of solar, then your mass to light ratio is only 1/6 of the Chabrier value. So if you assume a Chabrier IMF to work out your galaxy mass or your baryonic masses of your galaxy, you'll overestimate the mass in that galaxy by a factor of 6. Okay, so Carlos, mentioned this morning, so thankfully I don't have to talk too much about this. There have been some galaxy formation or cosmology calculations in the past that have played around with different IMFs. So Carlos's work on top heavy IMFs that he talked about this morning. More recently, it was work by Barber, Crane, and Shea, looking at both the effects of bottom light and all top heavy IMFs on galaxy formation simulations. And so I've teamed up with Rob Crane and his new student Anna Durant to work towards putting these sorts of metallicity, redshift dependent IMFs into galaxy formation calculations and then see how this alters galaxy properties. And just here a graph from Anna Durant. This is showing here that at redshift 7, you've got a significant population of stars that's forming here with a metallicity of greater than 1/10. And so there's potential here for this to be a bottom light stellar mass distribution. And so I'll just stop here, except to point out that I think numerical simulations are now able to predict variation of stellar properties, at least at the low mass end of the IMF. We still have to work to get into the high mass end of the IMF. But we can start to use these detailed star formation simulations to derive prescriptions, which we then give to galaxy formation people, for example, to put into their models. Thank you very much.